Have you ever wondered what would actually happen if a nuclear bomb went off in space? In the vacuum of space, you wouldn't get a blast wave like you do on Earth. So would it just be a silent flash of light that shines for a moment? Or would something happen that defies our common sense? Something you could never see on Earth? The truth is, more than half a century ago, humanity detonated a nuclear weapon in space just once. And the result was a mysterious aurora and widespread electronic failures. In this video, to answer this unknown question, we will explore everything together, from the basic principles of a nuclear explosion to the differences between one on Earth and in space, and even to a grand perspective that connects to the very creation of the universe. What is the principle of a nuclear explosion? First, let's get a handle on the mechanics of a nuclear blast. There are two types of nuclear explosions: fission and fusion. And the mechanism for generating energy is different for each. Nuclear fission is a phenomenon where a heavy atomic nucleus, like that of uranium or plutonium, absorbs a neutron fired from outside and splits into two or more lighter nuclei. During this process, a part of the nucleus's mass is converted into energy, releasing a tremendous amount. The atomic bombs dropped on Hiroshima and Nagasaki at the end of World War II were fission bombs. The principle is that when a uranium nucleus splits, it releases high-speed neutrons, which then cause a chain reaction by splitting other uranium nuclei one after another. By making this chain reaction proceed all at once, an immense amount of energy is released in an instant, causing an explosion. Nuclear fusion, on the other hand, is the opposite process, where light atomic nuclei combine or fuse to become a heavier nucleus. A typical example is the reaction where hydrogen nuclei fuse to become a helium nucleus, which is exactly what happens in the core of the Sun. In the Sun, hundreds of millions of tons of hydrogen are converted into helium every second. And in that process, a part of the mass is converted into energy. Nuclear fusion requires an environment of extremely high temperature and pressure, but once it starts, it produces energy that far surpasses that of nuclear fission. A bomb that uses nuclear fusion is a hydrogen bomb. It has a two-stage structure, where a fission bomb is used as a trigger to compress and heat the deuterium and tritium inside, causing nuclear fusion. An explosion from fusion has an exponentially greater power than a fission bomb of the same weight. In the largest hydrogen bomb test in history, the Soviet Union's Tsar Bomba, in 1961, an estimated 50 megatons of energy were released, which is about 1,000 times that of the Hiroshima bomb. 1 megaton is 1 million times 1 ton. Now, let's compare the energy scale with familiar examples. For instance, if we take the energy of 1 ton of TNT exploding as a baseline, the Hiroshima-type atomic bomb from World War II had the energy equivalent of about 15,000 tons. On the other hand, the aforementioned Tsar Bomba was equivalent to an estimated 500,000 tons, reaching about 3,000 times the power of the Hiroshima bomb. These are staggering numbers. But the scale of the natural world is on another level entirely. Every second, the Sun converts about 4 million tons of its own mass into energy, and its output in a single second is comparable to tens of millions of Tsar bombas. In other words, humanity's largest nuclear explosion doesn't even amount to a tiny fraction of the Sun's energy release. That's just how much of an incredible energy conversion nuclear fusion entails. The effects of a nuclear explosion on Earth. Next, let's organize the effects that occur when a nuclear explosion happens on Earth. That is, within the atmosphere. The destructive effects of a nuclear blast are well known and consist of three main elements: thermal rays, the blast wave, and radiation. Regarding thermal radiation, at the moment of the explosion, the nuclear reaction creates a fireball with a temperature of millions of degrees. This heats the surrounding air to incandescence, emitting an intense flash and thermal radiation. The light from a nuclear explosion is orders of magnitude brighter than the sun, instantly illuminating the surroundings with a brilliance greater than daylight. The fireball that forms immediately after turns the air into a plasma state and expands to a diameter of several hundred feet to several miles. In Hiroshima, people within a radius of 1.2 miles from the hypocenter suffered severe burns from these thermal rays. The heat rays continue for several seconds, during which they can ignite flammable materials, causing massive fires. In a nuclear explosion, this burning effect accounts for a large portion of the destruction. Regarding the blast wave, immediately after the nuclear explosion, the high temperature, expanding air creates a violent pressure wave in the surroundings. This is the blast wave. Near the hypocenter, it becomes a shock wave, exceeding the speed of sound, causing immense physical destruction to buildings and human bodies. Additionally, after the fireball pushes the air away, creating a near vacuum cavity, the surrounding air rushes back in to fill it. This causes a suction effect and generating secondary winds. In Hiroshima, buildings within a 1 to 2 mile radius of the hypocenter were destroyed by the blast wave, and people were blown away. A nuclear explosion generates a blast wave on a scale incomparable to conventional bombs, and its shock can be felt even tens of miles away. A nuclear explosion also releases a massive amount of radiation, specifically initial radiation, such as neutron and gamma rays, is emitted, penetrating deep into the human body and destroying cells. After the explosion, fission products and radioactive fallout are carried high into the air with the mushroom cloud and rain down over a wide area. These contaminate the environment for a long period and cause radiation damage to living things. In Hiroshima and Nagasaki, many who were not killed instantly by the blast wave or thermal rays later died from acute radiation sickness, or years later, they died from leukemia and cancer. A nuclear explosion brings not only instantaneous destruction, but also the invisible threat of radiation. Why does a mushroom cloud form? One of the images that comes to mind for many people when they hear nuclear explosion is the mushroom cloud. This is formed by the massive updraft and downdraft column created by the fireball after the explosion. Specifically, the air, intensely heated by the fireball, rises rapidly, and a ball of fire, several miles in diameter, ascends into the sky. This rising fireball acts like a giant hot air balloon, reaching altitudes of over 12 miles near the stratosphere. As it rises, a column of smoke and debris is pulled up from the ground behind it. The dust and city debris, lifted by the updraft, form a long stem beneath the fireball, which eventually combines with the spreading cap of the fireball. This creates the shape of a mushroom. This phenomenon is unique to large-scale explosions in the atmosphere and has become a symbolic visual of a nuclear blast. There is another special effect of a nuclear explosion called EMP. EMP stands for electromagnetic pulse, which is a powerful electromagnetic wave generated at the time of the explosion. Particularly in high altitude or large-scale ground-level nuclear explosions. The initial gamma rays interact with the air and the Earth's magnetic field, this instantly releasing an intense electromagnetic wave over a wide area. This EMP can induce excessive currents in power lines and electronic devices on the ground, potentially paralyzing electrical infrastructure and communications. In fact, during a high-altitude nuclear test in 1962, damage was recorded hundreds of miles from the hypocenter. Streetlights went out, and telephones stopped working there. The EMP from a nuclear explosion is like an invisible lightning strike that can destroy modern society's electronic devices in an instant. These are the main effects when a nuclear explosion occurs within the Earth's atmosphere. The presence of the atmosphere as a medium allows heat and a shockwave to be generated, a mushroom cloud to form, and an EMP to affect the ground. So, how do the characteristics of a nuclear explosion change in the vacuum of space, where this medium does not exist? This is where we get to the main topic. Let's finally answer the question of what would happen if you set off a nuclear explosion in space. What happens if you set off a nuclear explosion in space? Space is a vacuum. What would happen if you detonated a nuclear weapon in this vast expanse with no air and almost no gravity, a world without a blast wave? First, the most critical difference is that no blast wave is generated. On Earth, a blast wave occurs because the air transmits it as a shock wave. However, in the vacuum of space, there is no air medium to compress and transmit. The high temperature, high pressure gas produced by a nuclear explosion simply expands, as there is no surrounding air to push against and create a shock wave. Therefore, even if you set off a nuclear explosion in space, you won't get a blast wave that can blow away buildings like on Earth. To put it extremely, if there are no objects nearby, it's a quiet explosion that pushes nothing over, the fireball and flash in a vacuum. But does that mean it's completely harmless? Of course not. The vast energy from nuclear fission and fusion, even without a medium, is released in all directions as electromagnetic waves, light, and radiation. At the moment of the explosion, the nuclear weapon itself and its internal materials are heated to tens of millions of degrees, becoming a plasma fireball. In a vacuum, this fireball itself expands and cools in an instant, but the light and radiation emitted from it spread out into space spherically, with nothing to block them. An instantaneous flash of all wavelengths and particles, from visible light, infrared, and ultraviolet rays, to even X-rays, gamma rays, and neutron rays, is emitted all at once, traveling through space at the speed of light. Visually, from a distance, it would look like an ultra-bright point of light, like a camera flash, shining brightly for a moment. Since there is no surrounding air, the fireball doesn't linger, and the brightness of the explosion decays very quickly, since neither sound nor a shockwave is transmitted. If you were to witness it directly while wearing a suit, your vision would flash white in complete silence. This scene could truly be described as a silent explosion. The threat of radiation, however, being silent, is far from being safe when it comes to a nuclear explosion. In space, while there's no blast wave, the radiation itself travels directly over long distances. For example, intense gamma rays and X-rays can reach hundreds of miles to artificial satellites or astronauts in space, potentially destroying equipment or causing radiation sickness in people. Also, High-speed neutrons and other particle beams travel in a straight line for long distances without an atmosphere to slow them down. In short, when a nuclear weapon explodes in space, all its energy is unleashed in the form of light and radiation, reaching very far without diminishing. Additionally, while on Earth, an EMP is generated through interaction with the ionosphere. It's considered that a direct EMP is less likely to occur in outer space. However, it has been pointed out that if there is a planet with a magnetic field nearby, like Earth, the emitted gamma rays could collide with that magnetic field and generate a large-scale electromagnetic pulse. In fact, in past high-altitude nuclear tests, an explosion in space did cause an EMP effect on the ground through the Earth's magnetic field, phenomena not seen on Earth. So far, we've explained that a nuclear explosion in space is a silent flash where light and radiation spread out spherically without a blast wave. So, what is the supernatural phenomenon mentioned at the beginning that can never be seen on Earth? The hint is the aurora. It's known that a large-scale nuclear explosion in space can cause strange light phenomena in the environment around Earth. The prime examples are artificially generated auroras and the formation of radiation belts. We'll look at this in detail in the next chapter. A nuclear explosion in outer space might sound like science fiction, but it was a real nuclear test conducted in the past. The most prominent example is the high-altitude nuclear test Starfish Prime, conducted by the United States on July 9, 1962, the Starfish Prime incident during the Cold War, to demonstrate and study the power of nuclear weapons. Both the U.S. and the Soviet Union conducted nuclear tests in the atmosphere and in outer space. Starfish Prime was the highest yield space nuclear explosion test among them. Specifically, a 1.4 megaton warhead, mounted on a rocket launched from Johnston Atoll in the Pacific Ocean, was detonated at an altitude of 400 kilometers in space. An altitude of 400 kilometers is close to the orbit of the International Space Station, ISS, and is essentially outside the atmosphere, in what we call outer space. So what happened in this experiment? The explosion occurred at 11 p.m. Hawaii time, high in the sky above the horizon, as seen from the Hawaiian Islands. The results were a series of bizarre phenomena that exceeded all expectations: the flash and the artificial aurora. First, the flash from the explosion was so intense that even in Honolulu, about 1,400 kilometers away, the night sky lit up as bright as day. And immediately after, a mysterious veil of light spread across the sky. An artificial aurora appeared in the upper atmosphere, and bands of red and crimson light covered the heavens. This phenomenon was not only observed above the hypocenter, but was also seen at a corresponding location in the southern hemisphere, near Tonga in the South Pacific, on the opposite side of the Earth's magnetic field. This is believed to have been caused by the massive number of high-energy electrons released at 400 kilometers altitude, which traveled along the Earth's magnetic field lines and excited the upper atmosphere, causing it to glow. A nuclear explosion had artificially triggered a global-scale aurora, large-scale EMP, and its impact on ground infrastructure. After the explosion, a more powerful electromagnetic pulse, or EMP, than expected was generated in Hawaii. Despite being about 1,400 kilometers away, it caused disruptions to communications and streetlights. Specifically, damage was reported, such as telephone, microwave relays being burned out, and fuses in streetlights being blown. Since equipment at the time had no EMP protection, its effects were starkly revealed. As mentioned earlier, while there is no direct blast wave in space, the intense electromagnetic waves generated by gamma rays in the upper atmosphere destroyed ground infrastructure from so far away, making people aware of the threat of a space nuclear explosion. Satellite failures due to an artificial radiation belt. Even more serious was the artificial radiation belt formed around the Earth by the explosion. High-energy electrons were captured by the Earth's magnetic field, forming a belt similar to the Van Allen belts that surrounded the Earth for some time. As a result, radiation levels in Earth's orbit increased for several months, causing multiple artificial satellites to fail. In fact, in the months following the test, more than 6 satellites, including the U.S. communications satellite Telstar 1 and the UK's first satellite, Ariel 1, ceased to function one after another. This was presumed to be damage to electronic equipment caused by the radiation released by the nuclear explosion. The very space environment itself was contaminated and destroyed by a momentary nuclear test. Taking down the geostationary communication and scientific satellites that humanity had just launched, long-term effects on the Earth's magnetic field. Starfish Prime also had a temporary effect on the Earth's magnetosphere. The aforementioned artificial radiation belt was stored within the Earth's magnetic field, and the aurora was also a phenomenon that occurred along the magnetic field lines. Fortunately, these effects subsided over time, but one misstep could have risked making Earth's orbit unusable for a long period. This experiment delivered a major shock to scientists and governments at the time. It was the first time it was clearly demonstrated that using nuclear weapons in outer space would have devastating consequences in a different way than on the ground. As a result, in 1963, the Partial Test Ban Treaty was signed between the United States, the United Kingdom, and the Soviet Union, moving towards a ban on nuclear tests in the atmosphere, in space, and underwater. Furthermore, the Outer Space Treaty of 1967 prohibited the placing and deployment of nuclear weapons in outer space. Starfish Prime became a lesson for humanity that a nuclear explosion in space must never happen again.
The Sun, a colossal natural nuclear explosion.
Now, let's change our perspective. In fact, the sunlight we bathe in every day originates from the same fundamental principle as a nuclear explosion. This is because the Sun and other stars are celestial bodies, where nuclear fusion reactions are constantly proceeding in their cores. In the Sun's core, at an ultra-high temperature of about 15 million degrees, hydrogen nuclei are ceaselessly fusing into helium. Every second, about 600 million tons of hydrogen are converted into helium, and in the process, about 4 million tons of mass are converted into energy. This could be described as a kind of controlled, continuous explosion. As we touched upon with the example of the fusion bomb earlier, the nuclear fusion of hydrogen is an extremely energy-dense reaction. The Sun is a natural nuclear fusion reactor that contains this process with its own gravity, stably radiating light and heat. Occasionally, the Sun experiences a large-scale explosive phenomenon called a solar flare. A solar flare is a phenomenon where magnetic energy stored near sunspots on the solar surface is suddenly released, emitting powerful X-rays, ultraviolet rays, and particle beams. The energy is so immense that it is said to be equivalent to millions of 100-megaton hydrogen bombs exploding simultaneously. In other words, energy on a scale that even all the biggest bombs created by humanity combined couldn't match is occasionally released on the sun's surface. Furthermore, there is a phenomenon called a coronal mass ejection, or CME. This is a phenomenon where a vast amount of gas and magnetic fields are ejected from the sun's corona, its upper atmosphere, into space, often accompanying a solar flare. A giant CME can release tens of billions of tons of plasma, making it one of the largest explosions in the solar system. These solar flares and CMEs are cosmic explosion phenomena, and they also affect the Earth. For example, during the Carrington event of 1859, a giant flare and CME caused the largest geomagnetic storm in recorded history to hit Earth, causing auroras to appear in night skies around the world and telegraph systems to short out and catch fire. In 1989, a solar storm caused a 9-hour blackout across the entire province of Quebec, Canada. In this way, the explosive phenomena from the sun's nuclear fusion rain down on us as cosmic rays and geomagnetic storms, posing a risk to our technological society. In summary, the sun can be considered the ultimate nuclear explosion device. The gentle sunlight we see is in essence a product of the explosive energy of nuclear fusion, and phenomena like solar flares scatter energy into space on a scale that far surpasses humanity's nuclear weapons. When we look to the cosmos, we see that nuclear explosions are not the sole patent of humans, but are the very pulse of the stars themselves. A nuclear explosion near a black hole. Now let's consider an even more extreme situation. What would happen if you set off a nuclear explosion near a black hole? A black hole is a celestial body with super high density and immense gravity. Its gravity warps the surrounding space-time, and from inside a certain boundary, the event horizon, not even light can escape. If you set off a nuke in such a place, what would happen to the energy? Just imagining it feels like science fiction. Time dilation due to the gravitational field. Near a black hole, a relativistic effect called time dilation occurs where the passage of time slows down due to strong gravity. From a distant observer's perspective, things closer to the black hole appear to progress more slowly. A nuclear explosion is no exception. It is thought that from a distant observer, the flash of an explosion that occurred near a black hole would be redshifted by gravity. Its energy would decrease, and it would appear to shine faintly over a long period of time. In other words, the same nuclear explosion would appear to happen in slow motion near a black hole, and its energy would seem to have diminished. This is a phenomenon that occurs because gravity robs photons of their energy and stretches time. Does the energy disappear or get sucked in? If the light and particles released by the nuclear explosion were to enter inside the event horizon, they would never again appear in the outside universe. A black hole is a one-way trapdoor, and the classical view is that energy and matter that fall inside can never come out again. Therefore, if the location of the explosion is too close to the black hole, a portion of the radiated energy will be swallowed by it. The debris and plasma from the explosive itself would also be captured by the black hole's gravity and fall inward. In that case, from a distance, it might appear as if part of the explosion went missing and less energy was released. However, the energy doesn't completely disappear. The amount absorbed by the black hole is stored as the black hole's mass energy, and theoretically black holes also evaporate by emitting a tiny amount of energy in the form of Hawking radiation, though it's thought to be an extremely slow process. It's also predicted that smaller black holes in particular have more intense Hawking radiation, and at the end of their lives release all their stored energy at once in a final high-energy flash. However, such small black holes have not yet been observed and remain purely theoretical. Gravitational lensing and the appearance of the explosion. A nuclear explosion near a black hole would also be accompanied by visual wonders. One of these is the gravitational lensing effect. A black hole's gravity warps space, so the path of light passing through it is bent. If an explosion occurred near a black hole, the light it emitted would travel through warped space to reach a distant point. So depending on the observer's position, the light from the same explosion might be seen from multiple directions. It's also possible that a ring of light, an Einstein ring, could be seen around the black hole. This is an application of the phenomenon where a black hole bends the light of a background star into a ring shape. How the flash of a nuclear explosion would appear around a black hole is a very interesting topic, but unfortunately, it is still an unknown realm that humanity has not yet observed. Relationship with jets and high-energy phenomena. Another consideration is that matter falling into a black hole often generates powerful jets. The supermassive black holes at the centers of galaxies can eject plasma jets at near the speed of light from both poles as gas spirals down into them. The matter and energy from a nuclear explosion are negligible on a cosmic scale. But if the energy of an explosion were added to the accretion disk, the disk of gas around a black hole, it might temporarily affect its radiation and jet activity. For example, the high-energy particles generated by the explosion could heat the gas in the disk or disrupt the magnetic field structure, possibly causing an unusual X-ray flare. That being said, the energy naturally emitted by a black hole is on a completely different level, so a nuclear explosion would likely be a drop in the ocean and might not have a significant effect on the grand scheme of things. In summary, a nuclear explosion near a black hole would appear weak and slow from a distance due to time dilation and energy loss effects, with some of the energy being captured by the black hole. However, the explosion itself would still occur locally, so if you were to be there, its intensity would be the same. Of course, if you were there, you'd probably be torn apart by the black hole before the explosion even happened. In any case, this scenario is extremely extreme and difficult to observe in reality. But the question of what happens when you input energy into an extreme gravitational field leads to fundamental questions in astrophysics. Since black holes are the strangest and most intense objects in the universe, perhaps even humanity's greatest energy, release a nuclear explosion is insignificant before them, with only a limited impact. Can nuclear explosions be applied to space development? So far, we have looked at the threat of nuclear explosions. But finally, let's touch on a slightly more practical topic of application. Is it not possible to use this explosive energy for space development? In fact, there was once a bold concept considered to fly a spacecraft using the propulsive force of nuclear explosions. Its name was nuclear pulse propulsion, commonly known as Project Orion. Project Orion. This plan, researched in the United States from the 1950s to the 1960s, was to propel a spacecraft by successively detonating small nuclear bombs behind it. A giant metal plate would be attached to the rear of the spacecraft to act as a cushion, absorbing the shock wave of the nuclear explosions. The idea was to detonate bombs at a high frequency, such as 1 per second, and let the resulting impulses push the spacecraft forward. Pop, pop, pop. The velocity change per explosion would be on the order of tens of miles per second, but by repeating it hundreds of times, it would be possible to reach incredible speeds. The advantage of nuclear pulse propulsion is that it can achieve both immense thrust and high specific impulse simultaneously. A conventional chemical rocket has an exhaust velocity of a few miles per second, but the plasma from a nuclear explosion can reach tens of thousands of miles per second. This means that, in theory, an extremely high exhaust velocity can be achieved, and at the same time, the energy of the nuclear explosion provides enormous thrust, allowing a large spacecraft to be accelerated in a short time. Estimates for Project Orion included plans for a manned mission to Mars or Venus and back in just a few weeks. Furthermore, with improvements, there were bold predictions that a nuclear pulse spacecraft could reach a few % of the speed of light, making a trip to another star no longer a dream. In fact, there were calculations that a Fission-type Orion could theoretically reach nearly 10% of the speed of light, and a fusion type could reach several tenths of the speed of light. If it had been realized, it would have been humanity's first interstellar ship. It was a truly romantic plan. However, this overly ambitious project faced various problems. Technical challenges. First, designing a spacecraft structure that could withstand the shock of nuclear explosions was extremely difficult. Even with a giant metal plate and shock absorbers to absorb the shock, it was questionable whether the hull and crew could endure hundreds of nuclear explosions. The effects of vibration and radiation were also serious. Also, if detonated on or near the Earth's surface, a large amount of radioactive fallout would be produced. So finding a way to safely get it into space was another challenge. In experiments, small-scale, non-nuclear explosion tests were conducted with prototype models, and the propulsion concept itself was confirmed. But a full-scale nuclear explosion test was, understandably, never conducted. Treaties and political barriers. The Partial Test Ban Treaty of 1963 and the Outer Space Treaty of 1967 made it an international treaty violation to cause a nuclear explosion in space in the first place. Even at the time of Project Orion, there was strong opposition to nuclear propulsion, and the image of launching while continuously detonating nuclear bombs near Earth was feared as bringing the proliferation of nuclear weapons into space. As a result, Orion could not get political approval and was forced to be cancelled in the late 1960s. Dispersion of radioactive materials. Even if it were operated in space, a small amount of radioactive material would be scattered into space with each nuclear explosion. If exploded within Earth's gravity well, some of it would return as fallout. And even in deep space, there is the issue of environmental contamination. There were also a mountain of safety issues, such as the impact if a bomb were to rupture in an accident. For these reasons, the Nuclear Pulse Propulsion Orion project was never realized. However, in recent years, research on advanced rocket propulsion using fusion energy instead of nuclear explosions has been advancing. For example, there is the concept of an inertial confinement fusion rocket, which would successively detonate fuel pellets with a laser to turn small nuclear explosions into propulsion, and projects for fusion engines that would directly obtain thrust using a magnetic confinement method. These are similar in purpose to Orion, but differ in that they aim to use the clean energy of fusion continuously. If a fusion rocket becomes practical, it will enable high-speed space travel with high specific impulse, similar to nuclear pulse propulsion, opening the way for manned Mars missions and future interstellar exploration. Even today, research on nuclear thermal rockets, which use heat from a nuclear reactor, and nuclear fusion, propulsion, is being considered at the national level, including in the United States and China. Using nuclear explosions themselves is off-limits. But by using the fire of the nucleus for peaceful purposes to go to space, humanity may one day use the phenomenal power of nuclear energy as a key to travel to the far reaches of the solar system, and then to other stars. Conclusion and philosophical questions. Up to this point, we have looked at a wide range of topics through the theme of nuclear explosions, from Earth to space and extreme environments. Finally, let's change our perspective a bit and reconsider the concept of explosion on a cosmic scale. For us humans, an explosion is a symbol of destruction and terror. A nuclear explosion has the power to annihilate cities and make people suffer. However, when we look to the cosmos, it can be said that the current universe would not exist without explosions. If we unravel the history of the universe, the birth and death of stars are accompanied by explosions. In particular, a supernova explosion is a spectacular, explosive event that occurs at the end of a massive star's life. A supernova releases energy comparable to the entire lifetime of the Sun in an instant and scatters the heavy elements born inside the star into space. Many of the elements that make up our bodies, like oxygen and carbon, and the iron and silicon of the Earth, were scattered into space by the explosions of past stars. If there were no supernova explosions, heavy elements would not have been released from stars, and neither the Earth nor life would exist. In other words, the explosion of a supernova was responsible for the creation and dissemination of elements in the universe, and sowed the seeds for the birth of life. To be even more extreme, the Big Bang, about 13.8 billion years ago, the great explosion of the universe itself, was the beginning of our universe. The Big Bang is different from a normal explosion in that it was a phenomenon where space itself expanded and energy and matter were created. But there is no doubt that it was the ultimate explosion. Without the Big Bang, there would be no time or space. So we too are products of an unimaginable explosion called the Big Bang. Black holes also seem like a quiet death at first glance. But as mentioned earlier, small black holes may eventually explode with energy and disappear. Also, when binary black holes merge, powerful gravitational waves and gamma-ray bursts, which are explosive energy releases, can be observed. Gamma-ray bursts, which are the largest energy phenomena in the universe, are thought to be the universe's biggest explosions, associated with the formation of black holes or the merger of neutron stars. These rarely occur, but when they do, they release a flash so bright it can illuminate a galaxy. Looking at it this way, the question arises, is an explosion destruction or creation? For humanity, the nuclear explosion was a symbol of destruction. But on a cosmic scale, explosions have also been a catalyst for creating new stars, elements, and life. An explosion itself is a violent release of energy. But as a result, order is destroyed, and a new order is born. From the elements scattered by a supernova, the next generation of stars and planets were born, leading to intelligent beings like us. In a sense, the universe has evolved into its current state through a repetition of explosions of various sizes. Finally, is an explosion purely destruction, or is it a form of creation in the universe? We humans have obtained the nuclear explosion as an undeniable force of destruction. But how we understand and handle that power will change the future from a cosmic perspective. Destruction and creation are always two sides of the same coin. Now that we have the fire of the nucleus in our hands, perhaps we, too, are playing a part in the cosmic story of creation and destruction. Thank you for watching until the end. If you found this video interesting, please be sure to subscribe to the channel and give it a high rating. Also, our channel, Cosmic Lab, has been able to grow steadily thanks to the support of all our viewers. Thank you so much for your continued support. We have set a challenging goal of reaching 100,000 subscribers by the end of 2025 and are working our hardest every day to produce videos. If you haven't subscribed yet, we would be grateful if you would subscribe and continue to support us. We'll be waiting for you in the next video.